All right, welcome back to Calculus. Today we're going to talk about these three special sign limits. So in the previous video, we talked about this special one, the first one, and in fact, we used it to show why this second limit is true. Now, this third limit is new. Basically, that's one way to define e. E is the base of the natural logarithm, like e to the x or log base e, natural log. This is one way to define the number e. Remember, e is just like 2.718 and change. It's if you type into your calculator, let's see. It's a irrational transcendental number, so it has a decimal expansion that goes on forever. But there's the first whatever 8 or 9, 10 digits of e. Okay, but don't let it bother you. It's like kind of like pi, i.e. they are these irrational numbers, but they are just a number. They're special constants. Okay, so we have four examples here. The first two look like are involving trig, so clearly it looks like the first one's going to involve our first special limit involving sine, and the second one has some cosines in it, so we'll probably end up using the that middle special limit. And then the last two look like they're going to involve that new one that involves e. So let's just hop right in and see what we can come up with. So example A, let's see here. So we have the limit as x goes to 0 of sine 2x over sine 3x. Now, in the previous video, we talked about, example A and B here are kind of similar, but the difference between A and B on this example is that there was a division by x. There was sine 5x over x, and so we had like the over x part, but in these new examples we don't have that, so that's a little different. But I think we can do? I think we can do our special form of division by 1 that we do so often. I think that's really going to be what the key here is. Now, what if we divide, or say multiply, the top and the bottom by a special version of 1, and that special version of 1 is 1 over x. In fact, if you want to get really, actually no, we'll do that next. I was gonna combine another step here, but we'll do that next. So this right here, this is simply a special version of 1. It's a function divided by itself. That's 1. Assuming x is not 0, which the function is already undefined as 0, so that's not a problem. And yeah, so we do this. Now, how can we rewrite that? Well, this equals the limit as x approaches 0. So now we are dividing the top and the bottom by x. So that's sine 2x over x divided by sine 3x over x. So now we have this ugly compound fraction. Okay, but remember we have what's called the quotient rule of limits, quotient property of limits, which says if you have a quotient, a limit of a quotient, that you can take the limit of the numerator and denominator individually. So let's see if we can rewrite using that property. So now we're going to have a big vernacular, that big fraction bar with a limit on the top and on the bottom. So we have the limit as x goes to 0 of sine 2x over x. And then we have the limit as x goes to 0 of sine 3x over x. Now remember, we have that more generalized version of this, which basically says, if you have the limit as x goes to 0 of sine blank x over blank x, that limit's still equal to 1 if it's a scalar multiple, and other versions, but scalar multiples for sure. Okay, so that means if I can get, say, a 2x down there, I know what the limit is. Well, I can't just put a 2 there and just out of the blue. I have to strategically multiply. Again, I'm going to multiply by 1. Okay? What special version of 1 will I multiply by? Well, what if I multiply by 2 over 2 right there? That's 1, right? But on the denominator, I need a 3 on there. Right here, I need a 3. So what if I multiply by 3 over 3 on the denominator? So I've multiplied by a special version of 1 now 3 times in this exercise. And again, that's a very common technique you should always think about when we're in this class. Now, what can I do? I can rewrite. I have the limit as x goes to 0. Now, I need to rearrange this. In fact, what I'm going to do is I'm going to put the 2 on that denominator right there. And then the same thing with the 3. Put it right there. Okay, so now my limits are in the correct form, but I still have, that 2 right there, and I still have that 3 right there. So what do? I use the constant multiple rule to factor the 2 out of the numerator limit, and then we just have sine 2x over 2x, and then do a similar thing on the denominator. I factor a 3 out, and then I have the limit as x goes to 0, sine 3x over 3x. And now I know what those two individual limits are. Yeah, due to our special limit, I know this limit is 1, and I know this limit is 1. And then we have the constant multiples out front, and so we simply get 2 times 1 over 3 times 1, which of course simplifies to 2/3. Okay, simplifies to 2/3. All right, what else do we have here? Example B. You know what? I think example B requires the same basic tool. So we have the limit as x approaches 0. We have 1 minus cosine x over sine x. Now, remember, what are we working with? We're working with our typical properties of limits, and then we have these 3 special limits now. I think we're probably going to end up using both of the first 2, I believe. Because I have a 1 minus cosine x, which if I can get a 1 minus cosine x over x, well then I'm in business. And think about this. If I have a sine x, what if I get a sine x over x? And again, we have the limit as x approaches 0, so we are in the business of using these 2 special limits. Now, how can I do that? Well, again, what if we think about dividing the top and the bottom by x? In other words, multiplying just like we did before by 1 over x divided by 1 over x. We're multiplying by 1. So what does this give us? This gives us the limit as x approaches 0. On the numerator, we have 1 minus cosine x over x. And on the denominator, we get sine x over x. And then, okay, we have the 2 special forms almost. And we just now need to apply the limit quotient property. Because technically speaking, we don't know what the limit overall is. But we can take the limit of the numerator and denominator individually, and we do know what those are. So let's see. We have now a big fraction with a limit on the top and the bottom. Limit as x approaches 0. We have 1 minus cosine x over x. And on the denominator, we have the limit as x approaches 0 of sine x over x. And now I do know what each of those limits equal. The top limit equals, well, 0. Because we've memorized it, or almost memorized it. We'll soon memorize it. And the denominator, well, the limit as x approaches 0 of sine x over x is 1, which of course reduces to 0. So that one required both of our special trig limits. Now, C and D, we have to change gears a little bit. C and D are definitely harder as far as the limits are concerned, because we're going to use a technique called substitution that we have not really used, at least in limits, before. We've used this technique elsewhere. You've used it, say, in different types of equation solving and such, but we've never used it in terms of a limit before. So here's the idea. We need to somehow transform, let's look at example C first. We need to somehow transform this limit such that we can take advantage of this limit. And it might not at all be obvious how to do that at first, but I think a clever substitution will do the job for us. And that substitution, we need to choose a new variable. T is customary, but really any variable will do, anything besides x. So take your pick. I'll use a t here. So what I'm going to do is apply the substitution. Apply the substitution, t equals the numerator, e to the x minus 1. Now, I've worked this problem before, so I'm kind of familiar with what needs to happen since I wrote this book. But this is just one of those techniques you need to have up your sleeve. We'll use this technique of substitution a lot towards the end of class, so it'll really benefit you then. But just in general, when you're solving, sometimes complex problems in mathematics, substitution will sometimes help you if you need to, say, transform the function into a more suitable form. So what happens is we're not going to take a limit, but we're transforming, we're substituting the variable t now. Now here we gotta be careful. T approaches what? So we're not using x's anymore. It's mean the limit is t approaches something. Now let's put a note here. Note, as x approaches 0, t approaches what? In other words, think to yourself, as x gets closer and closer to 0, what happens to the left-hand side, sorry, the right-hand side of this equation? Like what happens as you get closer and closer to 0? In fact, what happens if you plug a 0 in? Well, if you plug a 0 in, you get e to the 0 is 1. 1 minus 1 is 0. So that tells me as x gets closer and closer to 0, e to the x gets closer and closer to 1. 1 minus 1, so the right-hand side gets closer and closer to 0. So in this case, we're going to take the limit now as t goes to 0. Now, sometimes when you do a substitution, you might get that the limit approaches some new number that wasn't the original value of c. But here, the value of c stays the same. But it's only true because as x gets closer to 0, t gets closer to 0. Now, let's think about how we can rewrite this limit. We know that e to the x equals t. So the numerator just gets replaced with a t. Now, it makes no sense to leave an x down there. And this is always true of your substitutions. When you're going to make a substitution, you need to transform the entire expression in terms of your new variable. So I need to go back to my substitution and say to myself, well, okay, let's erase that. If I know that this is true, what else does that imply? Well, if I want to solve that for x, I could say that implies that t plus 1 equals e to the x, yeah? I mean, just by adding 1 to both sides. And how would you solve this for x? Because I need to know what x equals. Well, if you remember from college algebra or your pre-calc, the way you solve this for x is by taking the natural log of both sides. And now hopefully this rings a bell that natural log of e to the x is simply equal to x, because natural log and e to the x are each other's inverse functions. So we could say that natural log of, I'm going to write this as 1 plus t, since that's the exact same thing, equals x. And now by substitution, I can go over here and say this is the denominator is equal to natural log of 1 plus t. Now notice, I'm kind of in the right ballpark now. I have a 1 plus a variable. That's good at least. Now I don't have the limit of 1 plus a variable raised to the 1 over that variable yet. I'm trying to get that form. I'm a good way there. Okay, and I think now just some clever rewriting will do the trick for us. So let's think about this. I'm gonna have the limit as t goes to 0. How might I rewrite this to where it looks kind of like this part? Well, there's a few different ways to do this, but here's how I like to think about it. How could I do this? What if I put a 1 right there? If I put a 1 right there, how could I use arithmetic to do something else? And here's what I mean by that. If I put a 1 right there, that means, what if I did like this? 1 divided by t right there. Like, is that the same thing as having a t on the numerator? That is 1 divided by 1 over t, right? If you do 1 divided by 1 over t, that's the same thing as you take the reciprocal of the divisor and multiply. So this would be 1 times t over 1, which equals t. So yeah, that is algebraically equivalent. And so now I have this 1 over t down here times the existing denominator, which was natural log 1 plus t. Okay, do you see where I'm going with this? Now, we recently used the properties of logarithms whenever we were solving logarithmic differentiation exercises. So if I give you that hint, do you see where we're going? Remember the power property of logarithms. The power property of logarithms says natural log of a to the x power equals x times natural log of a. Now usually we're taking the power and putting it out front. But if you have the scalar out front already, you can rewrite that as a power. So I can rewrite this as limits as t goes to 0 of 1 over natural log 1 plus t to the 1 over t power by moving the scalar of 1 over t out front to the exponent on the inside argument of that logarithm. Now, notice I have this form exactly. I have 1 plus the variable raised to the 1 over the variable power. And now I just need to apply the quotient property of limits to get the overall expression that I need. The quotient property says you can take the limit of the numerator and denominator individually. And so we're going to write a big fraction. So equals limit of the numerator. So the limit as x goes to 0. Sorry, this is a t. As t goes to 0 of 1, which that's just a nice constant. But on the denominator, I have the limit as t goes to 0 of natural log 1 plus t to the 1 over t. Now, notice I have limit as t goes to 0 of the natural log of 1 plus t to the 1 over t power. Notice there up here, there is no natural log. There is no natural log right there. No natural log. But I do have one more property of limits that's going to help us out. And we haven't used this one recently. It's the quotient not quotient, we've used that one. It's the composition property of logarithms. What does the composition property say? The composition property says if you have the limit as x approaches c of f evaluated at g of x, you could take the limit of the inside function first. and say this is f evaluated at the limit as x approaches c of g of x, provided that f is defined at that limit. Okay, so we do have a composite function here. We have natural log of this expression. In other words, there's understood parentheses right here. You know, if you don't see those, there's understood that the inside function is 1 plus t to the 1 over t power. Okay, so what we can do now is say equals. Now we still have, all right, let's go ahead and evaluate the limit up top. What's the limit as t goes to 0 of 1? Well, 1 is a constant function, so regardless of the value of c, the top limit is equal to 1. So we can just go ahead and evaluate that limit. That's nice, gets a little bit of the business out of the way. And then on the denominator, we can take the limit of the inside function first. Limit as, oh, did not mean to erase all that, but it's all right. Limit as t goes to 0 of 1 plus t to the 1 over t power. So I took the limit of the inside function first. And now here's the beauty of this. The beauty of this substitution is now I have this limit exactly, except for I'm using t's instead of x's. But that doesn't matter at all. Like just like we saw with like the limit as theta goes to 0 of sine theta over theta, it didn't matter if we used theta instead of x's. It was still the same limit. You know, the variable assignment does not matter at all. It does not change the answer. So I have the exact limit that I know from up above is equal to e. So I have 1 over natural log, and that limit of the inside function reduced to e. And now we just have a little bit of algebra to do. What's natural log of e? Well, this is asking us e raised to what power equals e? The base of the natural logarithm is e. So e raised to what power gives you e? Well, of course, the answer is 1. E to the first power equals e. So we get 1 over 1, which of course is simply equal to 1. Cool, that was a tough one. That was a tough one, for sure. Let's do one more tough one. Let's see, let's just erase all this stuff. I think we're going to do another one that involves that new special limit involving e. So let's see what we can come up with. Now I think we're going to have to apply a substitution again. And again, use this guy. So let's see, what might our substitution be this time? Well, let's first just rewrite the problem. We're going to have the limit as x approaches 1 of natural log x over x minus 1. I think this is actually maybe a little easy. Yeah, I think so. So let's see. We can do this. What about apply the substitution? Let's see. What about if t equals x minus 1? That might work. T equals x minus 1. So now we're going to rewrite the limit equals the limit as t approaches something. Now I know the denominator turns to now a t because I'm saying t equals x minus 1, which is the original denominator. Now, what does our limit approach now? So we always have to figure out what our new value of c is. So as the original limit, so as x approaches 1, t approaches what? In other words, what happens as x gets closer and closer to 1 with this original substitution? So t equals x minus 1. If x is really close to 1, then t gets really close to what? Well, if x equals 1, you get 1 minus 1, 0. So t approaches 0. So now our limit is going to be as t approaches 0. Now, again, like I said before, it makes no sense to write natural log x up there. We need to change the entire limit over in terms of t and not jumble up t's and x's. So the question is, how can I use my original substitution to figure out what natural log of x equals? Well, I guess in one sense you could say, well, don't even worry about natural log of x, just worry about what x is. Or you can figure out what natural log x is. I think you get the same thing either way. Let's see. You could either say, well, t equals, what if you add 1 to both sides? Sorry. You just add 1 to both sides, you get t plus 1 equals x. So you can either plug in for x, t plus 1 right away, or you could say, well, what's natural log x equal to? And take the natural log of both sides. Yeah, you get the same thing either way, which is, take the natural log of both sides, you get t plus 1 equals natural log of x. Or you can think about plugging in x equals t plus 1. Either way, it's the numerator turns to natural log of t plus 1. Or if you don't mind, I'll write that as natural log of 1 plus t. Again, we know that the addition of real numbers is commutative, so the order doesn't matter there. And it looks better because it'll match our limit up here better if it's 1 plus t. Okay. Now we're kind of at the same spot as we were last time. We want to get natural log of 1 plus t, or we really want 1 plus t to the 1 over t power. And how might we do that? Well, I think, again, a clever algebraic rewriting is going to be the key here. Because we're dividing this numerator by t. In other words, we can write 1 over t times the numerator. It's the same thing. Dividing by t, multiplying by 1 over t. But now we can use that power property of logarithms, just like we used on the previous problem. And we could say this is natural log of 1 plus t to the 1 over t power by applying that power rule of logarithms. And now we're to the exact same point we were on the previous problem, and we can now apply the composition property of limits, which says we can take the limit of the inside function. So it's going to be the limit of something and then taking the natural log of the entire thing. So limit as x, oh, nope, sorry, it's t, as t goes to 0 of 1 plus t to the 1 over t power. But now we know what that equals. We know, according to this special limit up top, the third one, that that limit is simply equal to e. So equals natural log of e, which of course we already discussed, is equal to 1. Okay, so those two last limits were on the tougher side. The first two were not too bad. I would say those are more medium difficulty. C and D were kind of on the harder scale because we had to use a substitution. But A and B were definitely on the medium side of things as far as the difficulty is concerned. So I'd expect homework problems, on the scale of A and B, maybe an occasional homework problem on the scale of C or D. Because I want you to keep up, keep that tool of substitution up your sleeve, keep it in your toolbox, because that will come in handy at periodic points throughout the class, using substitution. Here, let's be in the habit of checking ourselves using the graphical approach. So let's make sure our limits are correct. So the first one was what? Sine 2x over sine 3x. Now we said our answer was 2/3. It's the limit as x approaches 0. So 2/3 is like about 0.6 repeating. From the left, yep, or sorry, that's from the right. Obviously, we are undefined at 0. But from the left, we're approaching 2/3. From the right, we're approaching 2/3. So yeah, our limit is indeed correct. All right, the next one was 1 minus cosine x over sine x. We said the limit was 0, and yep, that screams 0 immediately. There is definitely a hole at 0, so we couldn't use direct substitution immediately, but the limit from the right is the y values are approaching 0. The limit from the left, the y values are approaching 0. And there's definitely a clear trend in the y values, just a hole at 0. Okay, what about the next one? Example C. Example C was e to the x minus 1 over x. Oh, just looks like the old regular e to the x function, basically. Okay. Hole at the origin, yeah, I mean, hole at x equals 0, yeah. But there's a clear trend from the left and the right. From the right, those y values are approaching 1. From the left, those y values again are approaching 1. So the limit definitely is 1 that we can tell from a graphical approach. Last one, natural log x divided by x minus 1. Okay, now this one we're concerned about the limit as x approaches 1. So yeah, we can see that if we hover over x equal 1, the limit is definitely, the function's undefined, but there's a clear trend in the y values. There's a clear trend limit that the y values are approaching positive 1 from the right, and from the left. So the limit was 1, which again verifies our answer. Cool. So, like I've said this before, it's very important to develop a graphical intuition for limits and for all of the derivatives and integrals that we're going to talk about in the future. So I would always be in the habit of checking yourself using Desmos, because chances are if you're doing homework, you're probably in front of a computer, so you can just log on to Desmos really fast. Graphing calculators, they're not very good at graphing, so I wouldn't. You could probably do the same thing on a graph, but it's harder to do because it's just harder to get a good graph. You have to play with the window a lot. It's kind of tough. But with Desmos, it shows a lot of features automatically for you, and so you can use that trace feature to drag a dot, and really helps with showing the limits. And again, we like to use the graphical approach to verify our answers. Okay, but we found all analytic solutions first. So. A couple tough examples, a couple medium examples. I think this is good. So in the next video, we'll talk some more about limits. If you need help between now and then, let me know. Always here to help. Otherwise, have a good one. I'll talk to you in the next video.